Okay, our next speaker is actually a pair of speakers. It's going to be Andrew Thomas and Sam Ventura. So Andrew Thomas has been on the faculty of Carnegie Mellon University Statistics Department since 2009 after he completed his PhD in statistics from here, Harvard. In fact, this very building. His main research focus is in the modeling of networks and relational data with focus on their uses in public and health policy. His research interests in sports are in hockey, baseball, and Scrabble, with emphasis on experimental design, variance decomposition, stochastic modeling, and a good deal of what-if thinking. Sam Ventura is a second-year PhD candidate at Carnegie Mellon University. His main research focus is in statistical and machine learning methods to improve disambiguation algorithms for data sets in need of record linkage. Sam is a native of Pittsburgh and is the captain of Carnegie Mellon roller hockey team. So thanks, guys.
Thank you, Mark.
Nice screen.
Oh, it's beautiful. All right. I think my computer hates me, so give me a second while I figure this out, while I patter a little bit. So actually, I just want to thank James for his very informative talk and how much I'm going to sponge off what he said to continue and motivate what we're doing in hockey. Yep, my computer hates me today. So I want to briefly thank a few people. First up is Shane Jensen. I don't know if he's here yet. So I can rip on him, even better. Shane was, let me just do it this way. Shane was very helpful. He's been spending some time at Carnegie Mellon over the last couple of months over the summer. Oh, I get one too? Thank you. We'll trade off. Okay. Shane was very helpful in unraveling some of these issues with big sports, and in particular with some of the hierarchical modeling issues. And so it's a shame I can't thank him personally today, but he knows what he did. Stephen Ma is an undergrad student of ours who has been preparing much of the data that we're going to be using today. Brian McDonald, who some of you may know, has done some other work in this area trying to extend these aspects to hockey, and it was his paper that brought our attention to the field, and we thought we would try and see what we could do with some of those concepts. Now, I wanted to depress James a little bit because I have a feeling that the algorithm might be okay in hockey, but I have another feeling it's going to be a little trickier. And part of the reason is that the data that you can get in hockey for this sort of event is a lot less informative, even though we've got what appears to be a lot of it. Now, at the very least, we still have some of these ideas that we were working with from the beginning. We have the idea of statistics, as most of the world knows it. You count up observations of things and you summarize them for player achievements. Everybody has known about these for centuries, or at least a couple of, at least one century, possibly more. And for judging these sort of player abilities, plus minus, as mentioned, was mostly the standard method that was used ever since the 1950s, even though it wasn't really public until the 1960s. We've seen other examples of regression and matching approaches to how you were able to tease out these effects. The Rosenbaum plus minus, the adjusted plus minus, is one of those. Brian McDonald's recently published paper in JQuas is another. There is another paper that I thought was really neat by Mike Schuckers and Denny Locke that dealt with taking events within the game itself and assessing point values to them in terms of goal scoring. Like, for example, you turn over the puck in the offensive zone. How likely are you to score a goal in the 30 seconds that follow that? And I thought that was a really neat way of accumulating a bunch of these little sorts of statistics, and possibly we can incorporate them into more sophisticated models a bit later. The other final approach that is probably less familiar to the bulk of the sporting community is the probability modeling approach. How you look at the game as some sort of process that you can use to infer when things are going to happen and how. So one particular thing that I was involved in a little while ago was just looking at the deviations from Poisson processes in hockey. How frequently are you going to see goals scored on one of these sorts of bases, given that other events are going to happen, like face-offs? This has also been done quite a bit in soccer. Hertz and Wright have put out a number of papers looking at these sort of Poisson modeling processes. Now, in general, we're looking at very, very simple types of data with this, usually just times until goals are scored. Now we have access to this much more sophisticated kind of information. In particular, what we're going to be looking at are the players that are involved in the game and the teams, and also maybe the score differential. So all these sorts of factors that are going to play into it a bit. Now, we've got potentially a lot of data at our disposal, given that there were, in our sample, 1,500 players in the NHL, each of whom who could have an offensive and defensive capability, let alone the teams, that there are currently 30 teams in the NHL that have the same appeal. So we would like to come up with some sort of model that's parsimonious. We'd like to be able to simplify it down quite a bit. What James was talking about with the hierarchical modeling approach, we'll do that to a degree. We'd also like it to be flexible enough that we could add or subtract things that we think are of particular importance. And player effects is the main one that we're going to get to. We'd also like it to be meaningful or interpretable in terms of a game outcome. And now, that can be a little trickier to perceive in terms of a regression model where you're just trying to tease out a beta coefficient. When we're putting together a process model, it's going to directly reflect what we think is the probability of scoring a goal within a particular time interval, given that a player is on the ice or a team is currently in this game. We'd also kind of like it to be predictive of future behavior, since that's really the goal for many of these sorts of studies and any kind of analytics, is to figure out who the valuable people are. Just because we can find an example in one time doesn't mean it's going to hold over until the next. So let me just bring up the Rosenbaum regression model for basketball, the adjusted plus minus. This is at least one of the simpler forms of what's going on. You have an outcome, which in this case was taken to be the difference in home and away points over the total number of possessions that were observed in an interval. Now, an interval that we're talking about here is typically between player substitutions. So every so often, you'll have a stoppage in play, you'll have a trade-off of one person from the bench comes on, one person on the court comes off. The typical way that this has been done already is to look at X as a simple indicator of whether a player is on the court for the home or away team, 1 or -1. And to really make this thing hum, we need at least some semblance of normality in the model. We need these extra error terms, these noise terms, to have something like a normal distribution, or at least close. Then we can use then our p-values are going to be valid, our central limit theorems are going to work. In particular, in this model, it was a weighted regression model, so that there was a grand sigma term, and there was a number of possessions that came into that. So the more possessions you had, the less the variance was, the greater the weight was. So this is at least a reasonably parsimonious sort of predictive model. No, thank you. Sort of predictive model that we could use for basketball. Now, there's at least two things that I want you to note here. Player substitutions happen very infrequently. Goal-scoring events happen very frequently. You'll see something like 20 goal-scoring events between substitutions. This is not quite the case for hockey. In fact, we have many more substitutions per second or per minute than we do in the NBA. We have many, many fewer scoring events than we do in the NBA. So the intervals that we would get under this approach are mostly going to be skating around for a while, trying to make some shots on goal, maybe a little fighting, or maybe it's a neutral zone trap, or whichever. We're not going to get a lot of real scoring opportunities in that time. For example, in this entire data set we have, which is 2007 to 2011, we have roughly 19,000 goals being scored in roughly 1.1 million opportunities. We're talking about a much sparser set of incidences than we would normally have. Now, what we're looking at is something like this. We have numbers representing players. We have each of these for the home and away. We have the time interval during which there were no substitutions made, much shorter than we're talking about in basketball. And we have whether or not a goal was scored by the home or the away team, 1 or -1 in this case. So given the fact that the data looks a lot like we had in basketball, we would think we might be able to turn it over a bit. And sure enough, for some of the data, we get something that looks kind of normal if we divide the goal scoring rate over the amount of time it took to happen. Now this is for 2007, when there were 5,127 total goals. Now, I've done something sneaky here and withheld the zeros. Anyone want to guess what the graph looks like when we put in the zeros? Yeah. That's one big middle finger from hockey telling us that we can't do this approach. So we're going to have to rethink this in another way. And in particular, hockey and soccer have given us this process model approach that's pretty good. It's been used pretty well to establish a number of things, including when to pull the goalie. It's one of the most popular approaches to figure out the timing of that one. And of course, they're still listening to us very much there, since no one has taken their advice. You should be pulling it much earlier according to these goals, but we can leave that for another barroom debate. So the approach we're going to take is the competing process model approach. So it basically says that there are at least 3 things going on. In fact, there could be many more, but we'll condense it to these 3. We have the home team is trying to score a goal. We have the away team is trying to score a goal. And we have player substitutions. So in total, what we're going to say is these are going to proceed independently until one of them happens, at which point we're going to reset the whole thing and start again. So in particular, let's say we were able to draw from this process. So we start each of them up, and we go until one of them happens, which in the first case is the time to a change was 28 seconds. So we then mark a change would have happened under this model. Then we start the whole thing again. Then we had a home goal and a home goal and an away goal and a change in the succeeding events, but we only observed the times for the events that happened. So probabilistically speaking, we only observed the shortest time, so we use the density for the event that we observed. And for the other 2, we knew it would have had to have been longer than that. So in our math, we're going to put in the probability that the time until the home goal would have been longer than the time observed, and the same for the away goal. And then we could switch these around depending on which event we observed. So in general, we could use this like a Poisson model. The simplest form is going to be like a homogeneous Poisson process where the time until an event is exponential with some particular rate. We can go a little more general, although for the time being, for the fact that goal scoring is so far apart compared to the speed with which the process reaches its stationary state. Basically, if you start at the very beginning of a game and you wait 2 minutes, I couldn't very easily predict whether you would be in the offensive zone or the defensive zone for one particular team, given what I knew about the face-off at the beginning. So the mixing is going to be good enough that a Poisson process is going to be adequate for the sake of what we're doing. And we've checked this a little bit with other sorts of models. So the typical approach that we can use for this is to say the home team is going to have some sort of scoring rate that's dependent on their offense and the opponent's defense. And the same thing for the away team, except the other way around. You're looking at the factors that can occur on offense for the away team and on defense for the home team. So generally, what we're going to do for this approach is just consider player changes to be exogenous. We know for a fact that they're going to be related to goal scoring in some very subtle ways. In particular, say you're going to in the offensive zone and the offensive team is pressing. It's very unlikely they're going to use this moment to change players. So there's a little bit of dependence between these processes. In general, we're going to ignore that, but we know we can take into account in later variations of the competing process. So there, I again mentioned a few of these factors that we can drop in. We've got difference in score. We've got the overall team ability. We have the players that play on each team, which may also contribute to overall team ability. So the next question to ask is, we've got this giant model. Do we really, really want to model all 3,000? Now, hierarchical modeling is pretty standard these days, as James has shown, as Shane Jensen has done with fielding as well as James. Baseball's done a little, baseball's been a big example for that when you're considering shrinkage to a common curve. So if you have any kind of noisy observations, you think they're going to be more similar to the group than you would normally observe just from the one noisy observation. So you could use the shrinkage model that James mentioned in this exact same way. Because you've got this common structure, you can impose this particular framework. We tried that the first time around. Anyone who saw this talk in August saw that we got some weird results. That was partly because some of the shrinkage effects that we were seeing were not quite identified as well as we would have liked. And also the data were wrong, but that's a whole other kind of story that we have to worry about. So for the time being, we're going to consider a slightly different approach and a different way of shrinking. I'm going to say that many, in fact, probably most players and or teams cannot really be statistically distinguishable from average. So in the process, we're going to use a method that says, let's estimate these parameters, but in a way that almost all of them within a particular position are going to be shrunk to 0. And in that way, we're doing variable selection at the same time as estimation. So sorry to all the average teams and players we're going to diss throughout the rest of the talk, but we're going to consider something along the lines of the lasso approach, for which I'll hand over to Sam. All right, how do I turn this off so I don't get a naked gun? Hands up. My time is up. His time is just beginning.
So as Andrew mentioned, we used the lasso to essentially shrink our estimates of player abilities to 0 whenever we're not confident that they are, statistically confident that they are any better or worse than average. And so you might have heard of lasso in the regression context, and that's essentially just a penalty function that pulls the parameters, pulls the estimates we have that we're not confident are significantly greater than or less than 0, and it shrinks them down to 0. In survival analysis, it's very similar, except we use a prior distribution, the lasso prior distribution, which essentially is just normal looking except with a sharp peak around 0. And so it's actually pretty easy to see in the following demonstration. And so the leftmost graph is the lasso prior, and so you see it has a sharp peak at 0. The middle graph is the likelihood function, so this is our estimate of the player's ability, and the rightmost graph is the posterior distribution of our estimate. And so you see that, so the posterior distribution is what we're most interested in. So this is going to give us, the peak of the posterior distribution is going to give us our estimate of that particular player's ability. And so we see that for a flat likelihood function, our posterior estimate is just going to be 0. Now, when we have a slightly sharper peak in the likelihood, we see that the posterior probability there's more of a kink around 0, and it's starting to split out a little bit. And so when we increase the size of that peak, we see more of a kink until the increase is enough so that when we combine the prior with the likelihood, the posterior estimate is different from 0. And so what this is going to correspond to in the hockey data context is players that have effects, posterior estimates that are significantly different than 0 are going to be players that typically have a large number of shifts in a particular season, or that are just so good that their estimate is different from 0. And these players are going to be players with a very small number of shifts. And so when we were picking this modeling approach, one thing we said was that we didn't want to have very high estimates for players who maybe only played 3 games but happened to produce a lot of offense in those 3 games, because we just weren't confident enough in those estimates. And so in that scenario, the likelihood curve is going to be a lot more flat, and so it's going to correspond to a posterior estimate of 0 because of the shrinking due to the lasso prior distribution. Okay? And so in real data, so this is data from the 2010-11 NHL season. The x-axis on this graph is essentially the strength of the lasso prior. And so a higher Laplace factor corresponds to a higher peak in the lasso prior distribution. The y-axis is just the offensive player ability for each of the roughly 1,500 players in our data set. And so this particular subset is players who have only had fewer than 200 shifts. And we see that for a Laplace factor of 3 or greater, all of these players are being shrunk to 0. And that's pretty much what we want. 200 shifts is not very many games in the NHL context. And so we see that for a small Laplace factor, these players have offensive abilities that are slightly different than 0. But as we increase this, the strength of that lasso prior distribution, they just get shrunk down to 0. And so what does this look like when we look at all players? So that's the the analogous plot for the defensive ability. When we look at all players, we get a much more cool-looking graph. And so, again, these are colored by the position of the player, so center, defense, goalie, left wing, right wing. The axes are the same in this graph, except now we have all players, not just players with fewer than 200 shifts. And we see that as we increase the Laplace factor, the estimates are starting to shrink towards 0, so the prior distribution is having more of an effect. But there are still those exceptional players who are standing out no matter how high we increase the Laplace factor. And so one very good aspect of this model is that it lets us pick out those players who are supremely confident in their estimates. And so again, for offensive ability, it's good to have a higher number and bad to have a lower number. And then the numbers closer to 0 are essentially just the average players or players who were not confident enough to have an ability estimate in. And so we see a similar trend for defensive ability. And so one thing we wanted to look at was if there was a relationship between the offensive ability of a player and the defensive ability of the player. So the first thing so the offensive ability is plotted on the x-axis and the defense on the y-axis. The first thing you'll notice about this is there's kind of this plus sign structure. And those are just essentially the estimates that were shrunk to zero. And that's why you see so many zeros along the axes here. And so there's a couple interesting things we see in this graph. First, it doesn't appear that there is any relationship between the offensive ability and the defensive ability. We kind of just see a scatter of points around zero. There's actually a little bit of bivariate normality here if you ignore the zeroed out coefficients. But the interesting thing from like a hockey perspective is that we can kind of see some clusters according to the positions. And so if you look at the goalies, which are the green points in this graph, most of them are slightly below average offensively, which makes sense because we don't think goalies are really producing any goals for their team. And most of them are above average defensively, which also makes sense because if you replace an average player with a goalie, then you would expect that the opposing team's goal scoring rate is going to go down. And so that's another thing to point out is that the defensive numbers, it's actually better to have a lower defensive number because it just represents the change in goal scoring rate of the opposing team when you replace an average player with that particular player. And so you want to decrease the goal scoring rate of the opposing team. And so that's why it's better to have a lower defensive number. So you also see things like it appears that there's more average centers and defensemen than there are average wingers. I'm not really sure what that means, but we also see some outliers off to the left there. So players that have very bad offensive ability and slightly bad defensive ability. And the reason for that is just because we use a very low Laplace factor, and so those estimates were not shrunk yet for this particular graph. Whereas if we increase the Laplace factor, we'd see a lot more estimates around zero and a lot fewer that were outliers. And so we bring up the question, who were the best players according to this model? And so I just want to put a disclaimer out there. Andrew's from Toronto, and I'm from Pittsburgh, and so we can definitely be accused of having our own biases towards our own players. But we definitely we made sure that that our model was right before we looked at any of the results to see who were the best players. And so it just turned out that some players from my city turned out to be a little better. I don't know. So the quote-unquote best offensive players are listed here. The reason I put best in quotations is because these are dependent on how strong the lasso prior is. So if we used a weaker lasso prior, then there would be some players that you might not have heard of, like a prospect for the Carolina Hurricanes when we used a very low lasso prior named Zach Dalpe turned out to be the best offensive player for some reason. But then when we increased the lasso prior, he was shrunk to zero because he only played in a handful of games that season. We also get to see who is bad on offense according to this model. And yeah, so one thing to point out was that if you look at the left wingers for the players that were bad on offense, we see that they all have zeros. So Justin Abdicator is not actually the worst offensive left wing. He just happens to have a name that starts with A. And so that's why he came up here. And so all this means is just the left wingers were all shrunk to zero for this particular Laplace factor. Defensively, we actually get a more interesting story. And so again, lower defense numbers are better. One interesting thing that I saw was that Patrice Bergeron of the Boston Bruins, who is known to be a very good defensive center, turned out to be a very bad defensive center according to this model. And we think that's because he plays on a team that has a lot of very good defensive players, such as Zdeno Chara and Tim Thomas. And so what's happening there is he plays a lot of shifts with other good defensive players, and so his rating is our model is saying that he is not as good as he really is. But some other interesting things here is that there were no bad defensive goalies. And there were a lot of very good defensive goalies. Tim Thomas turned out to be the very best defensive goalie in the 2010-11 season, which anybody who watched the NHL playoffs could attest to that. And so the point being, we can produce this output for a variety of Laplace factors, which essentially correspond to how confident we are in in each player's estimates. So in conclusion, we used a competing process model instead of the standard regression model because it sort of just fits our data well. We have an extremely large number of zeros. We have a smaller number of ones. So the regression context doesn't fit as well for the data set that we used, whereas the probability modeling process, the survival analysis idea, fits this scenario a lot better, and it actually takes that, it embraces those zeros and takes them in as information. Some things that we're looking into in the future is one, seeing if we can determine any interactions between players. So do the Sedines play better when they play together as opposed to when they play apart? Also looking at other events such as shots, hits, face-offs, things like that. And as Andrew mentioned earlier, going beyond the Poisson process and seeing if we can incorporate some other kind of process models into our framework.
We have time for a question or two. We'll keep it limited.
What's the motivation behind doing sort of the 30-second intervals after a turnover as opposed to the duration of the metric?
Okay. First of all, that wasn't my paper, but it did actually relate to other things that I've seen. If you were looking at, you can plot the probability of goal happening one way or the other for one team or the other over time in this whole plot. And as I recall, Chuckers probably knows this better than I do, but as I recall, that's at the 32nd point is where they leveled off, as where they both now had the same slope going upwards. So after that point, it didn't matter whether you're using one or the other. That turns out to be fairly consistent with this mixing time within the hockey game itself. Like 2 minutes after the opening whistle, you don't know what's going to happen. You could take that all the way down to 30 seconds, and you'd be just about the same. So that was at least the motivation there for why that timing was effective. That actually does tie into why this model is interesting and why the timing of it is useful in some ways. If we know in the game that there's something happening like a shot on goal, then we know that the probability is going to jump for the team that just did the shooting because they're closer to the other goal, and the other way around for the other team. So ideally, we can generalize this by including these other events because we know that we now have memory within the game with these sorts of things going on. So that's where that sort of thing comes into it.
How do you count for power play goals?
We omitted the part where we dropped the power play from the process. So for the sake of this particular model, we know that even strength obeys a particular process that we believe in. We have yet to adapt the power play model to it, although we suspect you could kind of do it the same way, as long as you had a little bit of that delay time. If a power play is going to be 2 minutes long, and we think that the natural time step of a hockey game is about 30 seconds, it's not at all clear it's going to be appropriate, but we might be able to approximate it. In the short term, I think it's fairly, easy is the wrong word, but you could, because you've got this fixed time interval, you could probably just count goals for and goals against a team on these sorts of units as a way of approximating these sorts of rate functions and then using the same likelihood sort of structure with lasso shrinkage to pick that up. But no, for the time being, we just worked with even strength 5-on-5 for stability's sake.
All right, let's stop here. You can ask these guys afterwards. So let's thank Andrew and Sam once more.